Yeah, don't forget to take one of the handouts. That's the last of the material I'm going to hand out. There's a fair amount of stuff in it, but don't worry, a lot of it is summary material that you won't find too difficult to handle. Well, we're a small group this morning, but I think we'd better start. You'll remember in Monday's lecture we were talking about oxidation mechanisms using extensive oxide phases as catalysts, and I gave first an illustration of how a variable valency oxide could function as a catalyst in a simple example, and then a more extensive and more complex example in which vanadium pentoxide doped with molybdenum was being used as a benzene oxidation catalyst. Just to finish off that topic, I want to point out to you, if we revert to sheet number 53, that it is possible to have an oxidation catalyst in which the active centers are not part of an extensive phase like V2O5, but one can put what one might regard as the essential component onto a support, and this is the illustration I have here, in which a vanadyl group, which contains 5-valent vanadium, is bonded through oxygens to a surface which might, for instance, be silica. We'll return later on, when we're dealing with molecular catalysts, to say a little bit more about that style of material, but I just want to point out to you that A, it's possible, and B, it doesn't necessarily give the same sort of catalytic behavior as does the corresponding extensive phase. And I've illustrated this with regard to V2O5, in which I point out to you here that V2O5, which we were dealing with in the last lecture, by and large functions as a partial oxidation catalyst. That is to say, you get significant quantities of oxidation product from hydrocarbons other than the oxides of carbon, whereas this material has catalytic activity all right, but it tends to be a total oxidation catalyst, with the products being CO and CO2. The mechanism of the reactions with these molecularly supported variable valency oxides are not well understood and they're subject of considerable work at the moment. But perhaps what I should point out to you is that the variable valency, when you're dealing with materials of that sort, is not accommodated via non-stoichiometry in an extensive phase, because the extensive phase in this case doesn't exist. But if one converted V5 here to V4, that change in valency of the vanadium would have to be accommodated via a change in the coordination number of the vanadium, and that would be brought about by the reductive process which reduced the V5 to V4. We'll return to say something more about that a little later. Let's now turn to another major class of catalytic active site functions, namely acidic and basic catalysts. Acidic and basic catalysts. Those of you who've had experience in organic chemistry will be familiar with generalized acidic and basic catalysis of organic reactions, in which mineral acids, for instance, or ordinary alkalis can be used to catalyze organic conversions. I'm not going to say anything about that. What I propose to do is confine the discussion to solid acids as catalysts, and confine the reactions to some typical simple hydrocarbon conversions which are of catalytic significance, particularly in the petroleum and hydrocarbon industries. Let's begin by running through this first sheet, which says something about the general situation. Of course, solid acids and bases are in the Bronsted category. Solid acids and bases are proton donors or proton acceptors in the usual way. The only point about it is that the acidic or basic phase is not in solution, but it's a solid. But nevertheless, these materials either donate protons or accept protons in precisely the same way as acids in solution. Surface OH groups may be acidic, that is they may function as proton donors, and a typical example is gamma alumina. Even silica has surface OH groups which have appreciable acidity, and that's readily demonstrated by the use of colour indicators, and the use of colour indicators for characterisation of the acidity of solids we'll return to towards the end of the course when we say something about catalyst characterisation. It is generally observed that strong surface Bronsted acidity is found with mixed oxide systems, and by far the most famous of these is the silica alumina mixed oxide system, which has a long history as a solid acid and a long history of industrial use which still goes on. The point about this is that if you form what amounts to a solid solution of silica and alumina, every time an aluminium atom enters into the lattice, in order to obtain charge balance, it requires an associated cation to neutralize the negative charge which the aluminium has to adopt if it's to become 4 coordinated. And so as a matter of simple valency, there has to be a cation, and the cation can in principle be a proton just as readily as it can be a sodium ion. In the case when the associated cation is a proton, it's generally thought that the proton is associated with one of the structural oxygens adjacent to the aluminium, and carrying a positive charge neutralizes the negative charge which the aluminium has to carry in order to, as I said, in order to become 4 coordinate. This structure here is really a two-dimensional simplification in the sense that the structure is basically one of tetrahedra which are linked together by sharing of corner oxygens. Now, this is a two-dimensional representation of what in fact is a silicon atom which is surrounded tetrahedrally by 4 oxygens. This is an aluminium atom which is surrounded tetrahedrally by 4 oxygens, and those two tetrahedra are linked together via a common oxygen atom by corner sharing. And although silica alumina, as it's normally prepared, is an amorphous material, that is to say it doesn't have long-range order, the basic structure of corner sharing is something like a reasonable description of it on a short range. And we'll find an extension of that notion of corner sharing in a few minutes' time when we turn to say something about zeolites. So silica alumina is a Bronsted acid because that proton is ionizable and it functions as an acid of considerable strength. It is, of course, it's also an exchangeable ion, and it can be exchanged for other ions if necessary. But while it's in its protonated form, it's an acid. Just very briefly, I should point out to you that, in effect, This protonated structure of silica alumina is thermally unstable. If silica alumina is heated to a sufficiently high temperature, it will split water out. It splits water out by, in effect, reactions between these quasi-hydroxyl groups, between the OH groups, and generates a Lewis acid, and this diagram here shows one possible scheme as to how Lewis acidity is generated. In fact, you have to rupture the structure. You get internal charge compensation here and generates a Lewis acid in which you've got an unfilled coordinated position on one of the aluminium atoms. In certain circumstances, the Lewis acid site may have catalytic significance. I don't propose to say anything about that. We're going to concentrate entirely on the use of Bronsted acidity as the catalytic function. Let me point out to you that this sort of acidity in solids is by no means the only way in which Bronsted acidity can be generated. There's been a great deal of work in recent years in which other forms of acidity have been generated in solids, usually by the use of acids which are themselves known acids, like sulfuric acid, and a typical example of this is sulfuric acid distributed over zirconia, which turns out to have extremely strong acidity, probably because there's a reaction product between the zirconia and the sulfuric acid of some sort of zirconium hydrogen sulfate, in which the hydrogen has very strong acidity. The actual structure is unknown. Or, as another example, SBF5, which of course SBF5 is known, if I might just scribble down here, SBF5 is known to form an extremely strong acid if it's in contact with hydrogen fluoride. This amounts to H plus SBF6 as being the acidic material, and that's been used in solution, particularly by Euler, for many years. But SBF5 on the surface of silica alumina gives extremely strong acidity. Again, the structure is not known, but it's probably some sort of ionic material of this sort on the surface of the silica alumina, where the actual groups that are coordinated to the antimony are not necessarily all fluorines. Just to remind you that if you have solid acids, you must also have solid bases. The next sheet, which I think I won't go through in great detail with you, but I'll leave you to have a look at it. It just reminds you that some oxides are strong proton acceptors. Magnesium oxide is a typical example, in which the surface oxygens react strongly with protons and are converted to OH groups. The basic reaction is as indicated here. The basic strength of magnesium oxide is very considerable, and for instance it's even possible with a magnesium oxide surface, particularly if it's been dehydrated by thermal treatment. It's possible to pull a proton out of ammonia, and ammonia is hardly a strong acid, and it's possible to pull a proton out of propylene, which is also hardly a strong acid. So it's a very strong base. We will say nothing more about solids as bases because we don't have time to treat everything. From a practical point of view, base catalysis using solid bases doesn't rival the practical importance of solid acids. However, although silica alumina is by far the most commonly encountered solid acid. It's by no means the only one. There is a vast range which have been studied, particularly by Japanese workers over the last 20 or 30 years. It's not well understood as to why in many cases the acidity occurs, but there is a general trend which I've provided on this diagram which says that if the acid strength is measured in terms of the Hammett acidity function, and I'll say a little more about that in just a moment, if the acid strength is measured in terms of the Hammett acidity function, there is a rough correlation between the average electronegativity of the elements making up the mixed oxide system of the metallic elements and the highest acidic strength of the solid acid. And the silica alumina system that we discussed a minute ago is right up here. And I should point out the Hammett acidity function is a rough indication of acidic strength. The more negative the value of the Hammett function, the stronger is the acid. I'm not at this stage, for those of you who have never seen the Hammett acidity function before, here's a rough summary of it. We're going to return to say something about the Hammett function in detail later on when we talk about catalyst characterization, so I won't speak in detail about it now, but you can have a look at that. And roughly speaking, the Hammett function relates to the pH of the acid solution. But the thing to remember is strong acids have high negative values for the Hammett function. And you can see there's a huge range there. And of the practical examples that are used industrially, silica alumina stuck up here as being a very strong, with a very highly negative Hammett function is by far the most common. Here are a few examples taken from practical materials in which the Hammett function, H0, is plotted against the amount of acid. In other words, these curves are distribution curves for the acidic strength. In other words, if I have a Hammett function of +2 for material A, 0.8 millimoles per gram is about the quantity of acid of that strength present in the system, present in the material. And all I want to point out to you is that, again, in these two systems, silica alumina in general and filtrol, which is a commercial silica alumina, have a roughly linear distribution of acidic strengths, but they go to quite high negative values, so the maximum acidity present is quite great. Silica magnesia, which has been looked at over the years as an alternative, is not a very satisfactory material from an acidic point of view, because the cutoff in maximum acidic strength is at quite a modest value. And the second of these illustrations compares some zeolites in the same fashion. Well, I'm going to say something about zeolitic structure in the next few sheets, but all I want to do here is point out to you that so-called Y zeolite, which is a phagosite structure, which we'll see in detail in a moment, in its protonated form has the acid distribution curve A, also running out to fairly substantial negative values for H0. If you cation exchange it, that is, exchange the protons for calcium, you get curve B. As expected, the total quantity of acid sites present is lower because curve B lies under curve A, but it's not entirely quenched. There are still acidic sites present, and so one has to conclude that the exchange does not actually get at all the acidic sites which are present in the zeolite. And if you exchange with lanthanum, you have this curve here. In the case of lanthanum, some of that acidity is due to some of that acidity in curve C is due to the fact that the hydroxyl groups, or the waters of hydration on the lanthanum ions that are then present in the zeolite are themselves acidic. And rare earth exchanged Y zeolite is an article of commerce as an acidic material, and the origin of the acidity in rare earth exchange zeolites is generally thought to lie in the presence of H2Os and OHs, which are ligands to the exchanged rare earth ions. Well, having started to say something about zeolites, let's continue, because they are now materials of considerable importance, and you need to at least have some elementary understanding of their structure and properties. Almost all the zeolites, well, first of all, I have to say what zeolites are. Zeolites are aluminosilicates. The basic structure being made up of linked tetrahedra of silica SiO4 and AlO4 with corner sharing in exactly the same way as I described for amorphous silica alumina. The difference between amorphous silica alumina and the zeolitic structures is that the zeolites are crystalline materials, whereas the amorphous silica alumina, as its name implies, is non-crystalline. Based upon the corner sharing of SiO4 and AlO4 tetrahedra, based upon that notion, it's possible to get an extraordinarily large range of crystalline materials. The number of zeolites which are articles of commerce is now, I would just as a guess, I would think at least in the low tens, perhaps somewhere between 10 and 30. The total number of zeolites which are known, which are distinct crystallographic structures, is well over 100, and a lot of these are now totally synthetic materials. That is to say, they are materials which are not known to occur naturally. Many of the original zeolites were obtained as minerals, and but virtually all anyway, have been subsequently synthesized in the laboratory. So the message is, zeolites are aluminosilicates based upon corner sharing, linked SiO4 and AlO4 tetrahedra based exclusively on corner sharing, and they are crystalline. When they are made synthetically, they are simply made in the obvious way, that is to say from aqueous silica solution, sodium silicate, aqueous alumina, usually aluminium sulfate, precipitate an aluminosilicate gel by pH control, sometimes the addition of so-called templates or crystallization control media at this point, and the aluminosilicate gel then undergoes crystallization, and very often in the process, if one wants to get a particular structure, it pays to seed with a specimen of the known structure that you wish to ultimately to obtain. The whole thing is a black art and highly empirical, but that's broadly speaking the way in which one goes about it. Now a word about how you represent structures, because unless you understand that, you won't make any progress. The bottom diagram here shows an example of tetrahedra linked by corner sharing. Tetrahedra linked by corner sharing. And that's a typical example of the way in which the aluminosilicate tetrahedra are linked together. The top part of this diagram is a ball representation of that structure, and the point of looking at it is merely to remind you that the oxygens are a relatively big ion compared to the metal ions which are buried in the middle of these tetrahedra. These balls are the oxygen ions, and at the middle of these tetrahedra are aluminiums. And so in this case, a tetrahedron consists of that oxygen, that oxygen, that oxygen, and that oxygen. And I've tried to show how they are tetrahedrally arranged by using by this diagram here, in which the dots, the points are supposed to lie at the centers of the spheres. And not shown, but buried in the middle of the tetrahedron is the metallic iron. The important point to realize is that when you draw a structure like as appears at the bottom, showing corner-linked tetrahedra, you need to realize that the amount of free space which that diagram implies is really mythical. It's really in that the actual structure is a much more close-packed structure than the ordinary than that simple tetrahedral diagram would suggest. Well, now with that to start with, let's have a look at one or two actual examples. First of all, this structure here. This is known as a silicalite unit. I'm sorry, a sodalite unit. And it's called that because it appears in an actual material called sodalite. The sodalite unit consists of an arrangement of linked tetrahedra. Appears at the tetrahedral structure appears at the top. The conventional representation for that is given here in a sort of a bond structure. And all I want to do is explain how this bond structure is related to the linked tetrahedral structure. Each of these bonds is drawn between the centers of adjacent tetrahedra. In other words, that bond there, that line there, is the line that joins the center of that tetrahedron and the center of that tetrahedron at the top, and you can't quite see it. Okay, so that bond is, or that line is that line there. So all of these lines that appear in this sodalite unit represent lines running between the centers of adjacent tetrahedra. In other words, they link together points upon which silica or aluminium atoms sit. And that's the significance of these line diagrams. Okay. That sodalite unit can be assembled in what amounts to a rather large simple cubic structure. When you do that, you finish up with the so-called sodalite material. Sodalite is in fact a zeolite, although not of much commercial significance, although you can in fact buy it. The problem with it is that, as you can see, the entrances or the channels which lie between the sodalite units are fairly small, and it's pretty hard to get molecules in. However, if you expand that structure a bit by sticking what amount to extra tetrahedra between the sodalite units, you finish up with a material called zeolite A, which is an article of considerable importance. It's not totally apparent from that, but in fact, within that structure, if you go in through that window there is a large internal cavity which is about 13 angstroms across. That window is relatively small. As I recall, it's around 4.5 angstroms. And so what you've got, if that structure is extended in all directions so that you get a macroscopic infinite crystal, what you have is a structure in which you have 13 angstrom cavities which are accessible one to the other by passage through windows of that size. And there are 1, 2, 3, 4, 5, 6 windows per cavity. And so a molecule enters through one of these windows at the external surface of the crystal. It's able to migrate throughout the structure, and it's able to occupy sites within the structure, to be absorbed, in other words, provided the size of the molecule is such that it's able to migrate through the allowed window size. And we'll say something more subsequently about the problem of accessibility depending on window size. So zeolite A is an article of commerce, although it's not used as an acidic catalyst, and I'll explain why that's so in a minute or two's time. If instead of arranging these sodalite units in this simple cubic structure, you stagger them, you finish up with this structure, which is the famous Fauger-site, or also the structure of Y zeolite and X zeolite. Both are used in ton quantities in the petroleum industry for catalytic cracking. Once again, although again it's not totally apparent from the diagram, but once again what you have here is a structure in which an internal void is accessible through a window. There's that window here, which is much larger than in the A zeolite. In fact, that diameter window on a van der Waals basis is about 7 angstroms. The void that you enter, the hole inside that structure is again about 13 angstroms across. And this structure extends, of course, in all directions to the boundaries of the crystal. And so, to summarize what you find in the Fauger-site or the X or Y zeolites is a channel it's a window and cavity structure in which a molecule which enters through one of these windows, which is present in an external surface of the crystal, is able to migrate throughout the crystal. And it will be able to do that provided the molecular size is such that it can get through a 7 angstrom aperture. Of course, in all of these cases, except for the sodalite and A zeolite, but in all of these cases of X and Y zeolites, on the internal surface of the zeolitic structure you have, if it's in a protonated form, you have protons present which render the material a strong Bronsted acid. And of course it's that Bronsted acidity which is the catalytic function which is used. Still some more to come, but we'd better make a start. In the last lecture, I was dealing with solid acids and their structure, including zeolites. And today I want to say something about some simple reactions which are catalyzed by solid acids. In all the cases we're going to discuss, the type of reaction involves carbocations, that is, organic entities carrying a positive charge, and these are generated by reactions that occur at the proton donating site of the solid acid. And the catalytic cycle consists of the generation of a carbocation at the acidic site of the solid acid, a rearrangement or some other reaction within the carbocation, and finally the cycle is closed by the donation of a proton back to the acidic site on the solid acid from which it first came. Just a very quick statement about terminology first. If we could have the overhead, please. Okay. Suppose I begin with an organic entity of that sort. Then I can, as a hypothetical experiment, do three possible things with it. If I remove an H- entity, it's called hydride abstraction, and one generates a carbocation of that sort, and that is referred to, that structure is referred to as a carbenium ion. It's not the only sort of carbocation that's possible, but it's a common one, and that used to be at one time referred to as a carbonium ion, but it's no longer called that. It's a carbenium ion, and the term carbonium ion is reserved for another type of carbocation. If instead of abstracting a negative ion, I abstracted a hydrogen atom, of course I would generate a free radical. And if I removed a proton from it, I would generate a carbanion. About these, we will, in this lecture, say nothing, but we're going to concentrate on the first of these. So a word, first of all, about the relative stability of carbenium ions. Essentially high-energy species, but the energy depends upon structure. And if, for instance, we look at a reaction of that sort, that is a gas phase reaction, for instance, in which a hydride abstraction is presumed to occur, it's possible to estimate the free energies of formation, these are delta HFs, on a relative scale for various ions relative to an arbitrary zero of taking the free energy of formation of CH3 plus equal to 0. The reason for the relative scale is that it's very hard to get absolute values, but it's not too difficult to get relative values. The first point to remember is that the stability of the ion increases with the extent to which the positive charge can be delocalized over the ion. And an example is here. An ion of this sort has a relative free energy, has a relative enthalpy of formation of relative to that zero, that is, of about minus 125 kilojoules per mole, whereas if there's a double bond in a formal double bond in the ion, the figure is a much greater negative value, minus 272 odd. In other words, this is a much more stable ion and much more easily formed. The reason why it's delocalized, of course, is that this is in effect as an allyl ion, and the charge is delocalized over the pi system of the allyl group. Within allyls, the main energy, within alkyls, the main energy difference lies between primary, secondary and tertiary ions, and here are some examples, again relative to this arbitrary zero. It depends on whether you have hydrogens or carbons attached to the carbon atom that's supposed to be carrying the positive charge, and you see that the stability of the ion increases in that direction where you go from a primary ion to a tertiary ion. And in fact, primary ions such as this nominal ethyl ion have such a relatively high energy that they're quite difficult to form under ordinary circumstances, although not totally impossible. So these are the two basic facts with regard to stability that you need to understand. With regard to structure of these simple ions, the ion itself becomes planar. That is to say, there's rehybridization on the carbon atom carrying the positive charge. It becomes planar, so the carbon atom carrying the positive charge is sp2 hybridized, and it's the p orbital which is vacant and carries the positive charge. Generally speaking, if you have external constraints which push the configuration of the ion away from a simple planar structure, the energy will increase. Now, something about how you form them. By far the easiest, and from the point of view of hydrocarbon chemistry, and probably the most important method of formation, is proton addition to an olefin. Here's an example. Proton is an electrophil. The double bond in an olefin is a nucleophilic center. And so the first interaction is probably of the proton with the pi system, but this is an intermediate, an unisolable intermediate, and this is the quasi-stable structure of the ion that's formed. You must understand that these things are not necessarily isolable directly in their, as simple entities. They're, generally speaking, these are reaction intermediates rather than isolable entities. It's not totally true that they can't be isolated, but at least they can be studied, and we'll say a little bit more about that later on when we come to talk about other systems. The positive charge is located to minimize the energy of the ion, and if you have a choice, then of course the system moves in the direction of minimum energy. Here's an example. Suppose you have a terminal olefin like propene. It could add a proton to give the positive charge being carried either by the terminal carbon or by the central carbon. That is, you could in principle have that, or you could have that. But we saw previously that when the positive charge is carried on a primary carbon of that sort, it's a high energy system, and in fact that's not formed, but this is the one that occurs in that particular case. then add a proton to an aromatic, and the carbocation, in the same sort of way, the carbocation then is usually represented in that structure. And I've made a note right at the bottom of the page to remind you that if you have ring substituents, not all of the positions in the ring are equal so far as the stability of the resulting carbocation is concerned. And in this particular case, which is metaxylene, the positions marked X are the favoured locations for the, actually that should be H plus, I guess, for the addition of the proton in protonation. In any event, proton addition to olefins, proton addition to aromatics, two very relatively ready methods of carbocation formation. Hydride abstraction. There are various ways in which the hydride, that's H minus hydride, various ways in which this abstraction process can occur, but they can certainly occur by interaction of a hydrocarbon with another carbocation. Now I've written the reaction out here, in which R1 plus pulls an H minus out of the hydrocarbon RH, produces R1H, and generates R plus. This, in effect, is a method of transferring the positive charge from one molecule to another. And in complex hydrocarbon reaction systems, it's a common occurrence. Whether it occurs to a substantial extent or not depends on the relative stabilities of the ions that are involved. And here's an example. If you contemplate reacting propane with a C2H5 ion, this is a relatively high energy ion. And if you look back at the energies of the ions that are concerned, the delta H for that reaction is obtained here as minus 96 kilojoules per mole. So on the basis of enthalpy, it's a favourable process. As you might guess, since you've formed an iso C3 cation of relatively low energy from a C2H5 cation of relatively high energy. The hydride acceptor can be a Lewis acid. Nominally, a reaction of that sort is possible. It's much more likely, however, that the entity which is pulled out of the reactant will be, in order for it to react with AlCl3, it will be much easier if the entity which is ripped out is Cl minus rather than H minus. That reaction is relatively straightforward and energetically favourable. And that really relates to the stability of that AlCl4 ion versus the stability of that one up there. Quickly, there are two others. One is heterolytic fission. Clearly, if you start, for instance, an alkyl halide, under thermal conditions it's possible to have heterolytic fission, although in fact that will be competitive with a homolytic process, and you can't be sure that this will be significant. The same thing might occur with an ROH. And finally, you can have hydride abstraction, what amounts to hydride abstraction under oxidative conditions, and really all this is a method of making the hydride abstraction reaction energetically favourable by a subsidiary oxidation process in which O reacts with H minus to give H2O and so on. Now let's say something about some typical reactions. A word about the history of all of this. Hydrocarbon reactions over solid acids has a long history. The first case in which reactions of this style were of industrial significance occurred in the pre-war years in the 1930s, when naturally occurring clays, which have some degree of solid acid behaviour, naturally occurring clays were used as catalysts in the petroleum industry, in cracking reactions, in that case, as I recall, in fixed bed systems. But it was not terribly satisfactory, but it was better than nothing. And the modern catalytic cracking process, more or less in the form we have it today, was developed during the war to produce high-octane gasoline. And it depended upon the use of synthetic silica alumina catalysts of the sort we talked about, but not zeolitic, amorphous silica alumina catalysts of the type we talked about in the last lecture. And much of what is known of the reactions of hydrocarbons on solid acids is associated with the cracking process as it's used industrially. Anyway, some typical reactions of which may occur in hydrocarbons via carbenium ions. What I'm doing here is simply picking out some very simple but I think typical examples of what can go on. The basic chemistry beyond this is very complex, and those of you who find yourselves requiring to know more about it will have to read it up separately. However, what can happen with a protonated olefin? Here's a carbocation which could easily be generated by protonating the olefin RCH